with the language side and the more neurocognitive aspect of it. I will every now and then do excursions to action processing and what we have in terms of neuroscientific evidence, but I will still come mainly from my background in neurolinguistics. And this comes from a proposal that I have developed together with Emiliano Zaccarella, another colleague, and Angela Friederici, and this has to do with what we consider to be a more meaningful computational approach to what distinguishes languages from other communication systems. And this has to do with this thing that I'll call labeling, and I'll define very at the beginning of the talk. So, to give you an overview of the structure of the talk, I will start by specifically mention what distinguishes language by defining also this labeling computation that I told you about, and what is uniquely human about it, then how it is implemented in the brain, specifically which brain areas are deal with the processing of these specific computations, and then how we can build parallels from this to other domains, in particular to action, and then if we really accept this computation as something defining for human cognition and for language, how can we test it in a way that it isn't inherently tied to language? Because otherwise we stay with a circular problem in a very Chomskyan way of, well, merge is for language, merge can only do language, you cannot find merge outside of language, so, well, good luck. So here you already have a bit of a disclaimer that I won't go full on Chomsky. So, what distinguishes human language from animal communication, and what in general distinguishes humans from other species? I will give you my answer to these questions, and I'm well aware that a lot of people will disagree, but I think that also from what we've seen in the last days, I don't think it's fundamentally about intentional communication, because there are aspects of intentional communications that we can see in other non-human primates. I also would disagree that it is fundamentally about any kind of symbolic faculty or abstraction, because, for example, in the Stroop task, we could see that there is at least a trace of it in non-human primates. And is it a limitation in sequential memory, in short-term memory? It is clear that non-human primates don't have such strong auditory working memory properties as humans, but that might be just a result of the fact that non-human primates don't communicate through long sequences of sounds. But if we look at other domains, there isn't clear evidence that non-human primates have a strong memory limitation. So I would say that if we take these apart, then it's more about how we combine symbols and how we hierarchically build structures out of symbols. And this brings me to the first of two disclaimers that I'll make at the beginning of the talk. I'll try not to judge other species from a merely human perspective, because this is not very helpful, and this is what is done in most of the cases. Of course, I will do it, but I'll try not to. And this brings us to I think that in these terms, what we heard yesterday at João Zilhão's talk was very important. Try to be aware of our own biases when interpreting the behavior of others, especially if we have no possible access to their mental content, which is very strongly the case of when we talk about other species or we talk of infants, the fact that we start inferring things about the complexity of their mental processes because of their surface properties. So, going for the linguistic start of the talk, we're now talking about linguistic trees. We're talking about combination of symbols and how they can then be transferred into sequences. And initially, what you have is Chomsky's proposal. And because I don't want, again, I want to avoid straw men, I'm giving you Chomsky's words. And Chomsky says that out of the fundamental capacity of humans is to combine two things into a unit and to combine them in an unordered way. I think that any cognitive psychologist or neuropsychologist would tell you, well, this is something that every neural system can do. Combining two things has really nothing special, especially if it's an unordered way. And also, even if they are of different characteristics, you actually have to define it a bit more than just merely combining. And this is the point where we say, okay, no, it's not only about putting two words together, because there is something about the combination of two words, and here in this case, how you combine the determiner the with the noun ship, is that when you combine the two words, the words themselves have a label, and the combination of the two words receives a label, which already shows that words are specific or particular objects. They have two sides. They are a handle for a specific meaning, but they also contain instructions about how you combine them, because these categories that words belong to are in the end rules that allow that allow us to know how we combine them, and then in the end the combination of the two words, this merged combination, has again the same property. You have a meaning that arises from the meanings of the two elements, and you have a label that also arises from the labels of the two elements. However, here they do differ because this label as because this label that the combination receives is the label of one of the elements.
I didn't want to. 1 minute. Go ahead. You have time.
So when you use these labels as anchor points, this allows you to create abstract hierarchies, and in production, so you combine words sequentially and you can create a complete tree the way we're used to see them. But it's also, and this is something that I find very important, and because language is for interaction, in my opinion, and against Chomsky, these labels are what allow you to go between the sequence and the hierarchical structure. Because if someone has a tree in their head and now are forced through a sequential medium to convey that tree, they will have to flatten it. And there is no way to retrieve, again, the hierarchical structure that you have in the sequence if you don't share some kind of code to retrieve back the hierarchical code, and that code is exactly in those labels. Because if you know the rules that were used to build the tree, you can now, from the sequence, retrieve the tree again. And then there is this very important point that you see in hierarchies or in the language hierarchies, and this is something that we will see again several times, is that then these hierarchies are points of asymmetry because exactly for the fact that the combination receives the label of one of the elements, now you establish a relation of dominance between the two elements. And also because what you do is to give a new label to the combination, now you have found an efficient way of compressing it, and now the new label can be combined again. So this is, in the end, what has been referred to several times as structural recursion, which is more than just the very, very superficial phrasal recursion of saying Mary said that, Peter said that, Mary said that, and so on and so forth. So if we take a long sentence like this and start, we have initially single words. And then from the strings of single words, you start to build simple combinations. And these simple combinations, they already have something hierarchical about them. But then if you combine them further, you see clearly that these asymmetries start to have a reality. So it's only by further combining words that you start having the full dimension of these asymmetries and of these hierarchical structures. And the idea was, from what we have been seeing, is that probably in terms of what we know about hierarchical processing, it should be around this area. Do we have a pointer?
Maybe the red one?
I think it's maybe off. Well. Okay. Around this area here that is in the inferior frontal gyrus that is dealing with these combinations. So the work by Emiliano Zaccarello, this colleague that I mentioned, was exactly trying to identify merge and labeling in the brain. So trying to see which brain areas reacted more to having two words that were combinable to two words that couldn't be possibly combined, or even abstract this to combining a function word to a word that doesn't have meaning, so an artificial word, also known as pseudo word. So again, going from the two words to the first and second combination, and what he could see in terms of brain activation was that for the minimal combinations of three words, so doing phrasal, what we would call phrasal merge, of having a prepositional phrase where you first combine the determiner with the noun and then combine the preposition with the determiner and the noun, you have the posterior part of the inferior frontal gyrus involved. And then if you go to the minimal combination, if you only look at the combination of the determiner with the noun compared to the combination of two nouns, you find again a peak in this area. And the fact is that if we go to the exact opposite and go to an experiment where people were trying to aim at this recursion that I was more or less making fun of, that is not really something that humans are very good at processing, because it has a very high working memory load. What we see is that, again, we see that posterior part of the inferior frontal gyrus being involved. And in my own work, what I tried to do is, okay, here we were using real words. What if we think that there are aspects about words that identify them in categories, maybe we can find a way of presenting people with pseudo words that sound very similar to words and can still be categorized as a verb, a noun, and so on. So we have a sentence that is built out of elements that don't carry any meaning, but they still appear to be either a verb or a noun or an adjective, and so on. And this in German is actually very easy to make, because words are phonologically very very typical. So it's easy. There are words. If you present this certain pseudo word to a German speaker, they will clearly identify it as being a noun or a verb or an adjective, because words sound like being a noun or a verb or an adjective, and also because the morphology, the inflectional morphology in German is very rich. It's also easy to identify them, because then on top of it you add the morphemes that are specifically to this. So as morphemes, I mean, for example, here this z that you have at the end of plays that identifies the third person singular in the present tense. And what we see is that if we have both syntax and semantics, we have this, what we would call in general the language network. We have this posterior activation in the temporal cortex, also extended to the posterior, to the inferior parietal lobule. We have the anterior temporal activation, the yellow part, and the whole inferior frontal gyrus involved. And then these are like the central areas of the language network. And then if we only look at syntax, so if we remove the semantic content, we see the posterior part of the inferior frontal gyrus being involved. Also, if we do a meta-analysis of studies looking at word lists or sentences, we see that in general, again, we see the inferior frontal gyrus playing a central role in the processing of these structures. So when we're talking about using natural language grammars, it seems that there is at least an aspect of structure building that we can abstract, and we more or less have a clear idea of what the underlying mental representation thereof is. And then and for us it seems to be that this labeling algorithm is what is underlying it. So the question is how to investigate this algorithm, and which aspects of this algorithm should we mimic. And here comes the second disclaimer. What I'm going to talk about is about artificial grammar learning, and at first I won't criticize it immediately, but there are a few questions about the following studies that I don't consider, or that we don't see as completely adequate to represent what we're talking about. So the idea of using artificial grammars was going beyond the question of using pseudo words. Was okay. Let's look at the mere combinations, the mere structures, and let's see if we can see differences between different grammars. I think that most people are familiar with these, and the idea was either we have grammars where we have very local combinations, or grammars where we have very distant combinations that have been called hierarchical. And if we go for these more linear grammars, we see that more like older parts of the brain react to them, whereas for more complex grammars, we see that also newer parts of the cortex, so parts of the neocortex, react to them. And these areas are also interesting because they have different connections. These older parts have rather ventral connections to the posterior part of the brain, whereas the newer grammars and newer parts of the cortex have a rather dorsal connection to posterior parts of the brain. And if we go for the evolutionary part, well, we see we find what would be obvious, that humans are, both humans and non-human primates can deal with these more linear grammars. If we go to these more complex grammars, usually, especially if we're not dealing with linear or adjacent dependencies, we don't see strong evidence from non-human primates being able to deal with them. And if we look at now at the connectivity between humans and non-human primates, what we see is that whereas humans show very strong dorsal connections between the frontal and the temporal cortices, in non-human primates you see strong ventral connections, but virtually no connections to the virtually no connections to the dorsal connections to the temporal cortex. And this is true for the macaque brain, but also for the chimp. And again, if we also look at comparisons in functional connectivity, especially from resting state data, because this is somehow or theoretically more comparable, we see that the main differences are in the inferior frontal cortex, and in particular in the posterior part of the inferior frontal cortex, which was exactly the one that we were talking about. And this, for us, points a bit in the direction that maybe there's something about maybe something about the connectivity. So it's about the white matter connectivity that might be a fundamental difference between humans and non-human primates for this particular issue. The fact that white matter connectivity remains flexible and that white matter remains in an immature state until much later in humans than it does in non-human primates could be an indication of how or of why humans are able to acquire this complex behavior later in development. And again, what we see is that, and on top of that, what we see is that this particular pattern that I'm talking about is something that is very accentuated in the prefrontal cortex, and there are obviously other differences and even more marked differences between humans and non-human primates in terms of evolution, in particular in the parietal cortex, and I would also be happy to discuss them later in the discussion in the end. But going back to the idea of the combinations that we find in language, going back to the combinations that we have in language, we have the operations that I talked about in terms of abstract structure building, so merge and labeling. We have then local combinations. We have something that is in language, it's not because you're able to always build a hierarchy about word combinations that these combinations are always something hierarchical. We can think about the combination of a determiner and a noun as something that is happening locally, at least at some point, and the fact that after a determiner, you don't, if you after a determiner hear something that shouldn't be there, which is the typical paradigm that you have in the early left anterior negativity. Some of these predictions that you establish in language are really about adjacent probabilities. So we should be aware that some of our language processing is very Markovian. And we also have the meaning associations that we find in conceptual combination that has been shown in different brain areas than what we see for more structural combinations. So in general, I would put up this sketch of where the different combinations are and what they represent. So in particular, the anterior temporal cortex has been shown to be very important in combination of meanings, whereas the posterior temporal and the posterior frontal have been involved in more abstract processing of structures, and this hints at maybe a duality in systems and their computations, whereas where you have in the dorsal system something that seems to be more rule-based, whereas in the ventral system you have something that seems to be more associative, also in parallel to what you find in the hippocampus in the formation of new memories, so also in the middle temporal lobe, and also in parallel to what we see in the models of procedural and declarative learning, which also seem to be more dorsal for procedural learning with support of the basal ganglia, and for declarative learning or declarative memory more ventral with support of the medial temporal lobe. So, getting out of language, can we draw parallels to other domains? So if we talk about this idea of the word duality, that words have a meaning and have and also have a label, and then these can be used further, we can abstract this to something that would be more general. That, for example, when we're talking about theory of mind, when we're talking about people's thoughts and their thought contents, and now we represent the thought content of another person. The thought as a representation of a thought is then a meta-representation. The same way that the verb phrase containing a determiner phrase is also somehow a meta-representation. And in developmental studies of theory of mind, of this second degree of theory of mind, what you see is that the same kind of connections that we see involved in the process of language are involved in the processing of theory of mind, and this is irrespective of their language capacities. In particular, the children that were investigated in this study weren't able to process the linguistic structures that would be necessary to convey their thought content in theory of mind. And then the other parallel that we can draw in terms of the asymmetry is that in particular these asymmetries that we find in language are usually the asymmetries between function words and content words, and especially the asymmetries between words that are more static in general. like nouns, and words that are more of a movement, like verbs or prepositions. And what we see is that here we also find parallels to action planning and tool use, because if we look at tool manipulation, you'll find also these asymmetries arising, and it's only the combination of these elements that allow you to, a combination of certain action with a certain tool that will allow you to then apply another action on this action tool combination. So if we look at action, execution, observation, and planning, unfortunately we don't have a very clear view. There is a lot of literature with prefrontal involvement, but the definitions of several studies are already strongly conflicting. In a recent meta-analysis done at the Max Planck Institute in Leipzig, we looked at different kinds of codings for action, execution, observation, imitation, and what we see is that for a lot of it, there is a clear involvement of the prefrontal cortex, not only in the execution, but also in planning. And there are many studies in terms of action planning that show that, in particular for human actions, we see an important role of the prefrontal cortex. And here what I'd like to say then is that there are several confusions that we have here when we talk about hierarchies and about asymmetries and the importance of linear order. The idea of hierarchy then, when we're talking about the observation of hierarchy and hierarchical behavior in other species, is about the fact that when we are combining symbols and when there are rules about combining those symbols, when you see, for example, this ABC structure, what happens is that when we hear this A, or when we see this A in the first position, we cannot combine the A with the B, because this B can only be combined with the C, and it's the combination of the two of them that can now be combined with A. So it's the fact that you have to put something on hold and then perform something else that is what actually is the observable side of hierarchy. The problem is that, what we see here is that now we establish a non-adjacent dependency. We saw that there is something that cannot be combined immediately, and every time that you have a hierarchical structure and force it into a linear sequence, these non-adjacent dependencies can arise. But the problem is that they are not themselves the diagnosis of hierarchy. You can have non-adjacent dependencies that have nothing hierarchical about them. If I say that the second element of a sequence has some relation to the fifth element of the sequence, there is nothing hierarchical about this. If I say that the second element of a sequence is the same as the fifth, what is hierarchical about this? Nothing. But it's a non-adjacent dependency, and this is what has been tested in the literature. And the same way that embedding isn't the diagnosis of hierarchy, as we see here in this sequence, and we heard an example of this yesterday, can I remember it? Michiro, who wasn't planned, came. This is not the real representation of the sequence. What we heard was Michiro, who wasn't planned, and this who wasn't planned belongs to A1, came. And this should be a T1. Sorry. And this is why these structures that have been investigated as non-adjacent dependencies and a representation of hierarchy are actually not really what we're doing in language.
Finish your time.
Okay, so then I'll tell you this, and then there's the fact that we really have to be careful in distinguishing what a hierarchical object, a hierarchical representation, and what hierarchical processing are. So here in the work of Martins, there's this complex structure that we see, and we see its hierarchical structure. The fact that this is a hierarchical object is clear because it was built in a hierarchical fashion, but actually it can also be represented in a non-hierarchical way if you pick this first one and add an hexagon to each end of it in an iterative way. And this is curiously something that we also do for language. So we don't do constantly hierarchical processing of language, and there was a very good claim that we had here that if we judged humans by the same criteria that we're judging other species, we wouldn't call ourselves also hierarchical processors, so to speak, because when we're processing language, we are also most of the times not doing hierarchical processing. We're basing a lot of the things that we do on semantics. If I hear something like eat an apple, I don't really need, or John eats an apple, I don't need to see the asymmetry between John and the apple because apples don't eat Johns. And we have a lot of evidence in this sense. So I'll skip to the end. So the idea is that if we want to really study these algorithms, we have to find a way to do this in a way that respects the capacities of the other species that we want to study, and also be clear about what we're testing and not testing something else as a proxy for what we are actually interested in. And for the case of action and tool use, I really don't exclude a scenario of coevolution of the two, and would like to discuss with you what you think about those issues. And I would just like to thank my collaborators, and in particular Natalie and Antonella, for having invited me.